Additive layer manufacture is a process whereby we take a computer-aided design of a component, we slice it up into layers, and then we build it up in layers. And you can see on this object here, we have layers of material added up, and we build up to make a whole structure. Here is the process in action. You'll see we have a robot with a welding torch attached. The robot moves the torch around in a pattern, depositing layers of metal. We use ALM because it has many benefits. In particular, if we wanted to make a part such as this one, it would normally we would take a solid block of metal, machine it all the way until we get the final part. With additive layer manufacture, we build up the part out from here, and we hugely reduce the amount of material that's utilised. This is particularly important in titanium components like this, where the energy required to produce the material is extremely high. Typically, you'd need 500 megajoules of energy to produce 1 kilogram of titanium, and this actually means that you produce 40 kilograms of CO2 for every kilogram of titanium that's used. The materials we can use in additive layer manufacture are very wide. We have a selection of materials here. This is a large aluminium part which was built for testing as a potential satellite component. We have standard steel components like this stiffened panel. This is a nickel alloy that's made very dense and high temperature material. And in particular, we're very interested in titanium, which is extremely expensive and difficult to work with. In the RUAM program, our main objective is really to produce high deposition rate additive layer manufacture so that we can make very large parts. So we might consider making whole aircraft out of this technology, hugely reducing the amount of material that's utilised in their production. We have several highlight results already. You can see here large complicated components have been made. We've made satellite parts out of aluminium, and a particular interest at the moment is we've been able to produce structures like this, which are in freestanding inclined walls. This one's at 30 degrees, and then we went down as low as 15 degrees, and finally we were then able to extend that to produce complete horizontal walls. And using this method, we were then able to produce fully enclosed structures. So this part here, the vertical walls were built up, and then we built the horizontal walls outwards. This is a completely innovative way of making this kind of structure and could have a massive impact in future manufacturing technology. We work with a wide variety of companies. Particularly at the moment, we're looking at aerospace companies like Airbus, EADS, Astrium, Doncasters. So these are all high value components, but we actually see wide range of applications in general engineering using basic steel systems as well.